Greetings to everyone. Now we are seeing about visual instrumentation presented by C. Pradeep. Visual instrumentation. It is defined as a system is a software that is used by the user to develop a computerized test and measurement system. A visual instrumentation system controls an external measurement hardware device from a desktop computer and display the test or measurement data on panels in the computer screen. A virtual instrumentation system also extends to computerized system for controlling process based on the data collected and processed by a PC-based instrumentation system. Especially, the engineers use visual instrumentation to bring the power of flexible software and PC technology to test, control, and design applications making accurate analog and digital measurements. The application ranges from simple laboratory experiments to large automation application. Now we are going to see about the application of virtual instrumentation. The application of virtual instrumentation is mainly three types. They are closed loop control, standalone monitoring, event response. Now we are seeing about closed loop control application. It is mainly applied and performed in aircrafts and data acquisition used to control DC motors, and this application is used to Quanset DC motor plug-in board for the LV kit and LabVIEW control, designing and simulation with LabVIEW MathScript RT, and traditionally tuning a controller requires multiple iterations and trial and error to perfect. However, LabVIEW allows you to tune your controller in real time and then move directly into verification with a seamless integration with hardware. This is a step 1. Step 1 is modeling the process. The first step to designing a closed loop control is to identify a mathematical representation of a plan or create a model. Many types of systems can model, including mechanical systems, electronic circuits, analog and digital filters, and thermal fluid systems. For these experiments, we are going to create model for a DC motor. The DC motor can be best represented by a transfer function. A transfer function provides a mathematical. The effectiveness and efficiency of virtual instrument design is largely due to the user friendliness associated with the programming process itself. Control flow is not the proper paradigm for an instrumentation environment. The asynchronous nature of instrumentation problem is far more naturally accommodated in a data flow based graphical environment. Thus, instead of conventional text based procedural programming languages where syntax and punctuation are the sensitive aspects of program, visual or graphic based program is ideal for visual instrumentation. Graphical icons are replacing text commands are simply wire connected to each other by means of a drag and drop operation. It simplifies the definition of the measurement procedure by means of object-oriented data-driven techniques. The measurement procedure is obtained by drawing a procedural diagram or a graph that defines the data dependencies and operations to be performed. The graphical user interface, that is GUI, presents a clear, logical, and visually appealing overview of the inner working of the entire program. Also, it simplifies program development, documentation, and maintenance and effectively reduces programming errors. Visual programming for visual instrumentation can be easily viewed as writing the block diagram of the measurement procedure by means of computer program. This block diagram is then translated into the computer executable code by some graphical programming compiler. The interpreter performs translation and immediate execution of the functional blocks without storing these in a file. This feature is very useful during system development to interactively test the procedure behavior without the need of completing the system definition, generating the executable code, and leaving the development environment to run an executable code itself. National Instruments LabVIEW and HPVE are the two popular graphical programming languages for the visual instrumentation applications. The use of virtual instrument integrates various measurement functions into PC-based control environment that otherwise would have been accomplished by several standalone measurement instruments which are generally expensive or may not be available in a realistic application environment. Also, replacing multiple instruments with an integrated virtual instrument increases the portability of the entire system while reducing the space requirement, which is of particular importance for test and evolution of launch vehicle avionics, as it needs shifting and setting up of systems at different locations for various environmental tests. Station concept introduced recently further this interchangeable virtual instrumentation concept introduced recently further reduces development time and also improves the quality of virtual instruments by incorporating some standards with this measurement subsystems from different sources would be having a standard connection and user interfaces so that this can be easily and directly built in measurement systems. It is using very complex measurement systems. The equation is given below to represent the model of our DC motor, where Km is equal to motor back EMF constant, Rm is equal to motor armature resistance, J equivalent is equal to equivalent moment of inertia. Assume that J equivalent is equal to Jm motor armature moment of inertia. Ohm m by Vm is equal to Km by J equivalent Rms plus Km whole square. This is the math script we are using here for the DC motor control. This model will be used to design a closed loop controller which can be tested with actual motor. We can represent this transfer function in LabVIEW by using a math script node, which is part of the LabVIEW MathScript RT model. The input parameters values were obtained from the Quanser QNET DC motor specification sheet. The MathScript node can be found under programming structures and palettes. Next, we are seeing the control design. This is the control design simulation loop. When designing a controller, it is best to fully understand the plan, in our case, the DC motor. This understanding comes from analysis of specialized graphs such as board, root locus, and Nyquist plot, which build initiation of how the plan will behave. Graphs in the time domain, such as the step response, provide immediate feedback on the ideal behavior of the system, such as rise time, overshoot, settling time, and steady state error. For this experiment, we will design a PI control for our DC motor using LabVIEW control design and simulation model. The simulation loop, which includes a built-in ODE solver for handling integrals and derivative terms, can be found in the control design and simulation palette under simulation. The simulation gain, integrator, and transfer function blocks can also be found in the control design and simulation palette under simulation, signal arithmetic, and simulation continuous linear systems. This is the block diagram of our DC motor control. This step, this is the block diagram of closed loop control to DC motor control. Here we are using the math script node and here we are using the control design and simulation loop. This step is simulating the module. This step is simulate the response of DC motor when modifying set point or desired speed of input. This will allow us to tune the controller parameters or gains to increase the robustness of our system. We will need to combine the transfer function or model of the DC motor that we created in the step 1 with our closed loop controller. And next is the tuning and verification part. And by using tuning and verification part, that we can simulate both the controller and response of the DC motor. We can follow an interactive iterative process to optimize our controller. We will tune the controller parameters from the LabVIEW front panel while verifying the system performance. In the There are two types of control designs and simulations. In control design, they conduct two types: tune control parameters and estimate performance. And simulation, they also conduct two types: introduce impairments and nonlinearities, verify performance. This is the synchronized process. We can use the following steps to tune our control parameters. Begin with gain set at Kp is equal to 1 and Ki is equal to 0. Here we set the value according to our wish by changing the desired speed. Based on the values the waveform will create. Increase the integral gain to reduce steady-state error if necessary. Once we run the program, we can see the desired motor speed and estimated motor speed plotted on the waveform chart. While the rise time looks good with our proportional gain Kp set to 1, the plot shows a small amount of steady-state error, which represented by the gap between the desired speed data and estimated speed data. We can reduce the steady-state error by increasing our integral gain Ki. If we increase the integral gain Ki to 10, we have a much better system response. This is the diagram of our implementation DC motor control, and this is the waveform for our speed control of DC motor. Now that we have verified that our PI controller works with simulated DC motor response, we can implement our finalized control system and control the speed of our Quanzer DC motor plug-in board for LV skid. The LabVIEW control design and simulation model can be used to control real-life systems as well as simulated models. To migrate from simulated control to real-life control, the plant model can be replaced with hardware input and output function. In this case, we will replace the transfer function representing the DC motor with data equation is called as DAC, input and output VIs that control actual motor, and migrate from simulation to real hardware by replacing transfer function with hardware input and output blocks. Timing is an important consideration when using the LabVIEW control design and simulation loop with real hardware. Since the control design and simulation loop uses a built-in ODE solver with time steps, it is important to set the simulation parameters and the timing parameters of the loop to have the same time step. Data acquisition tasks typically use timing parameters, so it is also important to equate the simulation loop timing with the data acquisition timing. Now we can run the LabVIEW program and control the speed of the Quanzer DC motor from the LabVIEW front panel. This is the output of the DC motor, and this is the implementation block.